So up until this point, we talked about representing numbers, representing characters, representing floating point numbers, doing operations on all of them. What we're going to do next is get into the machine level and talk about representing programs. How are programs represented, and how do they operate on all of your data? And we're going to use 64-bit x86 because that's what's ubiquitous on most of our desktop and laptops. Okay, so the prior edition, some of you have a prior edition of this textbook. The prior edition used 32-bit x86. We just recently shifted over everything to 64-bit. So this is why all the homeworks would be different if you have an older textbook. So there's that. So the Intel x86 architecture has been an evolutionary design about 40 or 50 years in the making, and it shows. With all of the cruft that's in this processor, it shows that it's had a long history. So the main versions of it that we can sort of point to as being sort of watershed moments in this architecture was in 1986, the 386 processor was the very first 32-bit Intel CPU that moreover supported virtual memory. And you can see already what an ease virtual memory is, because then every single program that you write, every process that gets executed, it thinks that it can own the entire memory space. You don't have to worry about using memory that some other process might have data in. And so up until this point, we didn't have the sort of the separation, the process separation that these CPUs supported. The next interesting iteration was this Pentium 4E in 2004, which was Intel's first 64-bit version of the architecture. And this was adopted straight from AMD. So AMD implemented it first, strangely enough, and then Intel adopted it. And then the Core 2 in 2006, this is where they realized they could no longer make the processor, the single processor, faster and faster. They hit a ceiling in terms of making that fast. And so they decided to just start putting multiple cores on a chip. And so up until this point, from this point on, then their speed-ups in processors are basically because we're adding more processors on the same die versus speeding up those cores. Okay. One of the features of the x86 architecture is every time you get a new CPU, you get a whole slew of new instructions. And these new instructions will target very specific applications that are hot. So, for example, the MMX instructions for multimedia, and we'll be looking at some of these later on, they are targeting the fact that video, when you process video, you're going to do the same operation on a whole bunch of pixels, right? So if you have a vector of data and you say, I want this operation to be sent to that vector, it would be nice if the CPU did that, right? This is called single instruction multiple data. And this is what different iterations of the x86 started adding. Other things that got added were memory protection for security. So x86 was riddled with security problems in the 80s and the 90s. And so they slowly started adding hardware features to protect against these memory corruption bugs, as you'll be exploiting in your assignment. There are new instructions for conditional data movement, and this is for performance. And we'll talk about this in 2 lectures, how these specific instructions make your program run faster. That makes the loops, for example, like if, then, else's and while loops, it makes those much faster than otherwise. And then obviously expanded address space, so from going from 32-bit to 64-bit. So a 32-bit system maxed out at 4 gigabytes of memory. And so we have well over 4 gigs at our disposal now, so that's what the 64-bit architecture helped. One of the drawbacks of this evolution is that now there's a whole bunch of obsolete features on the chip, but they still have to be in there, supported, for backwards compatibility. So there's a whole slew of floating point instructions that nobody uses anymore, but they're there and they're supported. Well, I think they deprecated some of them, but they have to support all of the instructions from the previous generation in order to keep it from failing. Backwards compatibility. Okay, so the Intel x86 architecture is known as a complex instruction set computer architecture. And so there are many different instructions with many different formats. This is the opposite from a reduced instruction set computer, where in a reduced instruction set computer, you have a very small number of instructions. And to implement the larger sort of instructions, you use multiple simple instructions. So the two dominant processors are Intel and ARM. ARM is a RISC. Intel is a CISC. And ARM typically has better memory or better power consumption as a result of not having to implement so many different complex instructions. That's one of the benefits of a reduced instruction set computer. So you have a very tiny subset of instructions that you implement, but you try and implement those very fast. So that's the notion. Whereas in Intel, so when you're doing like encryption, for example, Intel's like, wow, I want to actually build the entire encryption round as an instruction, and then they'll build it. And AES is an instruction in x86. And ARM is like, that's silly. I'm just going to implement that using smaller, faster instructions.
So which one has better performance?
The AES definitely does. So power consumption wise, the ARM is better, but raw performance, the x86, obviously, if you build that all into a specific circuit, and that's the encryption algorithm that you're using over and over for all the web stuff, then obviously you can get better performance. And it's it's not surprising that the servers are all dominated by x86, and then all the clients are dominated by ARM, because one is focusing more on raw compute power, and the other one is sort of like compute power per watt kind of thing. So.
And by ARM, you mean like mobile device?
Yeah, like the things that are in the iPhone. iPhone's an ARM. Most of these are ARM.
I think they're switching.
Oh yeah.
Someday they want to make their own actually too.
Oh, so they actually do make their own, but they license the instruction set from ARM, but they actually build their own custom designs around it. I'll actually, at the end of chapter 3, I have this little section comparing ARM and x86, which I'll get further into this at the end. Once you see everything in x86, then you can sort of translate some of these concepts into ARM. Okay. This is a picture of, I think this is the current generation. This is Broadwell. And you can see here's a couple of cores. You see a whole bunch of cache, and then now integrated processor graphics on this. One of the trends in computing is that a lot of the stuff is now happening in the graphics processor, and less is happening in the core in terms of speeding up computation.
Less and less is integer multiplication, right?
Yeah, you're doing a lot of vector stuff. Even this deep learning stuff is using this kind of stuff because it's a whole bunch of parallel computations, vector computations on data. But yeah.
So I heard somewhere, and it's kind of funny, that it's more efficient to have a bunch of even old processor, but a lot of them, rather than having one new one which has more cores. Let's say you have one which has 2 cores, rather than getting 2 processors at one. And I heard that that's actually
Power efficient or time efficient?
No,
I guess it's your...
operations efficient. Like if you want to do complex operations, it's actually more worth to buy more processors than actually getting one which has more cores.
Yeah, it would depend on how you would evaluate. Yeah.
How true is that?
It depends on the context. Like, what are you optimizing for? Would be what I would say. It depends. Yeah.
If you can salvage like a bunch of computers and you create your.
If you're optimizing for cost, you want to do that. If you're optimizing for peak throughput, maybe not. It depends on, and then cost, obviously. Cost, peak throughput, power. Those are the things that you would think about. Yeah, there is no one answer for that. Yeah. Well, this is so. Hopefully, you guys take the parallel programming course or the high performance course, because then the way you program these systems has to change. And so there are some programming languages that try to automatically parallelize your serial implementation, but in schools we don't really teach parallel thinking. I think sequentially. But that's one of the things that, well, if this is the way we're going to architect our computing systems, then the way you need to think about programming them is in parallel. Right? So, like Google has their MapReduce, which is a parallel algorithm for doing a lot of their implementing their searching algorithms. So that's sort of a newer way of thinking about algorithms that hopefully you guys will get to, because you'll need to get to that just because the underlying hardware is now highly parallel. Okay, so I've got my hardware. How do I program it? So initially there were no compilers, and there were no assemblers. I mean, there were like punch cards that you were punching in opcodes for the processor to act upon. And so you would generate this machine code by hand. And obviously this is not ideal. Like error-prone, time-consuming, hard to read and write, hard to debug. So the first thing that we did was generate these assemblers. And these are programs that would assign mnemonics to machine code, and then given the mnemonic like this, it would generate the object code that would then be executed on the processor. So it's basically a translation system that translates English text or English sort of characters into the object code that implements that. So for example, this is a move instruction, and move from the RAX register to the RCX register, and that would get, the assembler would take this and then generate the object code for that instruction. One of the real frustrating things about assembly code is that there's no standard. So in fact, Intel has their own assembly language for x86. The one that we're using on Linux Lab is the AT&T GAS assembler format, which is slightly different. Microsoft has its own assembler, which is again different. And one of the most annoying things about it is that the operands are flipped in the Microsoft version. So when you go back and forth, the source and the destination operands are the opposite. So sorry, there's nothing I can do about that. So moving RAX to RCX, this is source destination. This is the way we're, in this class, source is on the left, destination is on the right. So yeah, burn that in. That's what the AT&T syntax is. All right. So even with the advent of compilers, so this is actually sort of difficult to program. Like, you don't really want to be managing registers and managing memory directly. Like you're accessing the memory locations directly, the registers directly. This is still difficult, but it's actually still used. Hand-coded assembly is still used because oftentimes compilers, first of all, can make suboptimal code, right? If you're asking a program to take your high-level C program and generate efficient assembly, that's always going to be less efficient than hand-coded assembly, because humans can usually figure out how to code better. And so you find that a lot of the low-level operating systems were still hand-coded in assembly. You couldn't rely on a compiler to generate efficient assembly code. The other reason why you still use assembly even today is that anytime Intel releases a new processor with new instructions, well, the only way you can get access to those new instructions is to hand code the assembly for them, because the compiler technology takes a long time to incorporate new Intel instructions into the compilation process to generate that efficient code. So you end up hand coding the assembly and then integrating it with the rest of your C code. And this is what your assignment 3 is going to be. You're gonna embed some assembly code into your C program, and then hand code a vector operation that'll hopefully get 20 times improvement using this mechanism. Okay. All right. So after assemblers, then we develop the compiler, and a compiler will take a C program like this, and will generate assembly code that looks like this. So this is a one-to-one translation. Sum store is the function. It calls this function plus, and then the return value is t, and then some pointer is dereferenced. T is stored at the pointer to d, and then this is what it looks like. You can sort of see some of that in here. You see the call instruction. You see a move. That's basically what gets generated in the compilation. And this is what this chapter is about. I'm going to have you be able to decode this eventually. Okay, so with an assembly program, you have a specific view of the CPU state. And so this is abstractly what it looks like. So on the CPU, your assembly program has access to the instruction pointer, a certain set of scratch registers, and some condition codes that tell you the result of a previous instruction. And this is used for your conditional branching. So if you have x is equal to 0, you check. What's going to happen is that a subtraction is going to happen, and the condition code off of that subtraction is going to be checked to do a conditional branch on it. So that's sort of the CPU state that you get. As part of your machine state, though, you have a virtual memory address space. So every process has this uniform memory space abstraction, where it believes it has the entire memory space off in yellow. And in this memory space, this is where the program code is loaded in the .text section. This is where the program data is loaded in the .data section. This is also where the operating system is mapped into the process's address space. So the operating system code is part of this yellow thing. And also runtime data structures such as the stack. And the stack is going to be used for function calls, as we'll see later. But also the heap. So we saw the malloc instruction. Well, it turns out there's a region in this memory called the heap that all of those memory locations are allocated from when you do a malloc. And this is basically your flat array of bytes, and then you're allocating pieces from it. And so what happens is as the processor is initialized, as your process is initialized, the instruction pointer is going to point to the beginning of your code in main. And then the CPU is going to ask for instruction addresses and get instruction data back and then execute them. And as part of executing an instruction, it will also go back into memory for operands. And in the same memory space, your data is stored, and then data will come back. And so you see the CPU is hitting memory multiple times for a single instruction. Give me the next instruction, and then the instruction's got operands, and some of those are in memory, then it goes back into memory, give me the data, and comes back. And so you really want this pathway to be fast, right? You want to get to and from memory quickly. And so we'll look at that in chapter 6, how that happens. All right. So are there any questions about this picture? Does this picture make sense to you? Yeah.
You were talking about the operating system being mapped in like constants and stuff like that. So what happens, like, operating system calls and stuff like that?
All the operating system code is mapped into the high gigabyte of memory of every user's address space. Yes.
So what happens when you can actually change and use those to interact with programs? Because I know you can send system, like you can change system variables inside of a program and have that other system.
So here's the thing with the operating system. It has to make sure it has isolation. So even though the code is mapped into the memory space, when the user process goes into kernel mode and executes kernel instructions, it can't have any side effects that would in fact impact the other processes that are. So we call this. So I'm not going to talk about it in this class, but reentrant code is basically code that doesn't have side effects that you would have to pass in. Rather than it having state stored in it, you would pass in the memory locations that it would fill in, just so that processes are separate from each other. But I think that'll be in 333 when you take that. You'll see why. Okay. Here's a picture of the Linux 64-bit memory map. And you see all of these things. At the top part of memory in a user address space is where your kernel code, data, and heap and stack reside. And then you have a space for the user stack. You have a space for dynamically linked libraries that are loaded in at load time. So we saw dynamic linking. You go into the file system and you copy all the code for libc, for example, into memory. That's where this region is. And then eventually you'll patch up your code. If your code calls printf, you'll patch up your code so that when printf gets called, it'll jump into that memory space. You have the runtime heap. This is the space for malloc. You have your read-write segment. So this is for your program variables. They're global variables that got initialized or uninitialized program variables. And then your read-only data and your program instructions are loaded in a specific location. And so we saw before, this is it's like having an entire flat, array of memory of bytes. And then within that, you sort of carve out regions. And everything in the gray is unallocated. So if you try and access addresses in the gray, you'll get this segmentation fault. Because the process must have allocated everything in white in order for it to use it. And so, when you allocate space for it, you're telling the operating system to say, this virtual memory address, reserve some real memory on chip for this virtual memory address. That's what an allocation does.
So this is an abstract on top of physical memory?
Yeah, so virtual memory. So you have an abstraction that this process has a flat address space. But what the CPU and the operating system do is translate that into a real memory address, right? So you could have two address zeros, like process A has address 0, process B has address 0. When the CPU and the operating system look at that access, it has to translate that into a real address, and those real addresses will be different. And that level of indirection is how you implement virtual memory. To give that illusion. So that's the virtual memory layer. And I think in 333 you'll be looking at that. If on a Linux system you want to see this, you can do a cat of proc self maps. In fact, I could show you what this looks like. I'll go VM up. You can see the memory map for any process in the proc file system. So here's my process 1878. 748. Actually, I'll do proc self maps. That's not it. They changed it. Wait. Yeah. So this is the output of that command. Let me resize this. And so you can see the memory segments that have been allocated for, this is Z shell, my shell. You see the text segment. This is all the text code for the Z shell binary. And you can see up here at the higher address, these are the dynamic libraries that Z shell loads at runtime. All right. And then down here, you see the stack is over here. And then this stuff is your kernel. This is the syscall stuff. This is all your kernel memory down here at the bottom. It doesn't look like there's a heap anywhere. But. All right. Well,
So are those physical addresses?
these are virtual addresses for this process. And so they would get translated by the CPU and the operating system to a real address in hardware. And that's how you get that abstraction. So even though everyone's got the same addresses, and everyone could have the same, everyone could have the, how did I get that in cat maps? Everyone could be mapping into this 400,000 range in their virtual memory address space, but then it would get mapped into different physical memory addresses underneath, and you wouldn't be able to see those physical addresses.
And those are handled on the kernel level?
Kernel in conjunction with the CPU is going to map your virtual address into a real physical address.
So you utilize both.
Yeah, you need both. Yeah. In order to make it efficient, you need both. And this is what, the way this gets implemented will be what you're going to do in the operating systems course, how it's done. All right. Okay, so the next thing I'm going to talk about are registers. So we saw that abstract view of the resources. One of them was the memory address space. The others were the instruction pointer, the registers, and the condition codes. So let's talk about the registers. The registers are special memory that are not part of the main memory. So they don't have a memory address, a virtual memory address. You access them directly by name. They're located on the CPU, and they're typically used to store temporary variables. So if you have a function in C, and you say, within that function, you declare a temporary variable, more often than not, that thing, when the compiler compiles your program, that temporary variable will be implemented using a register. The compiler will assign a register for that temporary variable, and will use that register to update its value as you're updating that variable. It can be up to 64 bits. It's typically the width of the architecture, the word size of the architecture. So in 64-bit x86, it's 64 bits. In 32-bit, it was 32 bits. Yeah.
How about the rest?
For the things you showed before with the command, can you actually look at the memory at a certain virtual address? Actually examine it?
You can access that.
Would that be useful for you?
It would be useful for adversaries and good guys. Yeah, so yeah, you could directly try and modify, if you have the right permissions, the raw memory device, and then it would do that for you. Yeah, sure. In fact, there are ways of interacting with the /proc file system. So at runtime, if you want to change certain kernel parameters, you can just go into the proc file system and there's a variable there that if you change, will update the thing. It'll translate it into that process's memory address space. So yeah, that's the power of that particular proc file system. So use with care. Okay, so with registers, typically you would load data into registers and then manipulate them and then store them back into memory in your program. This is the set of integer registers for x86-64. There is a separate set of floating point registers that we'll talk about later, but for any integer argument like pointers, chars, ints, shorts, if you have those in your program and you're using them, they will end up being stored in these registers. And now you see in each one of these registers, there's the whole register, and there are subsets of these registers. The subsets are for versions of these registers in smaller bit sizes. So for example, this is 64 bits. If you access this register as EAX instead of RAX, then you just get the low 32 bits. And this is for backwards compatibility. Because we had 8-bit x86 programs, we had 16-bit x86 programs, 32-bit x86 programs. They need to be able to run on the 64-bit processor. So all of those registers that they were using have to be implementable on the 64-bit version as well. So that's why you see the different versions. There are the letter registers, A, B, C, D, and then SI and DI. And then there's a stack pointer and a frame pointer, and then these integer registers R8 to R15. And the reason why this is different than this is that this half got added with 64-bit x86. So it used to be just the ones on the left, and then they added the ones on the right afterwards. There's barely any registers, yeah. There's for the longest time, up until 2004, there was only these. These were all your registers that you had, that the compiler had to play with. Now, some architectures, like the Motorola processor, had 32 registers, 16 or 32 registers, and you're like, wow, the compiler was like, I can totally store a bunch of temporary variables in these registers and act upon them. Turns out there are trade-offs, and that might be good for the compiler, but it might be bad for efficiency. And in fact, I think the next slide, I'll get to that. Okay, yeah. We'll get to this. We'll get to this discussion later. In fact, the guy in particular who liked this was Linus Torvalds. He's like, keep this. Keep this small set. Don't put more in there. And there's a specific reason why he doesn't like the extra registers.
He doesn't like C++ too.
Yeah. There's no comment. I don't want to say anything about C++, but I don't code in it. So this is an expanded view of the RAX register, and you'll see these different mnemonics going across, and it's sort of painful to remember. But the RAX register specifies all 64 bits, and then you have the 32-bit version, EAX, and then you also have the 16-bit version, AX, and then you have the 8-bit version, AL, and with the 8-bit version, you also have the low byte and the high byte, AL and AH. So those are all the mnemonics for the same register, just different parts of it. So you might see some of these in assembly code, and that's where they are. There is a specific mnemonic that goes along with this, and we'll get to that later. Okay, so all of the registers on the left here have a similar way of accessing it. The other registers on the right are numbered from 8 to 15. And to access the different parts of these registers, there's a byte version, R8B, a word version, R8W, R8D, and R8 by itself is the 64-bit version. And the suffix, the W says low word, where they say a word is 16 bits. The B is low byte, where the B stands for byte, the W stands for word. The D stands for double word, which is 2 of these. And then the R8 is a quad word, so I don't know why they didn't put a Q in there, but that would be where, I bet you in the 128-bit x86, this turns into a Q, and then they'll do something else for them. Well, I don't know, actually. I don't think there will be a 128-bit.
Is that just updating your assembler to represent it?
Yeah, there has to be different opcodes to represent the fact that you're using either the 64-bit version or the 32-bit version. So that's part of the instruction encoding. Yeah. Okay, so let's get into this register selection. So initially, the x86 architecture was register poor. There were only 8 of those general-purpose registers to begin with on the left. And then this was initially driven by the fact that transistors were extremely expensive at the beginning. So before we were able to put billions of transistors on a die, it used to be that the transistor space was quite valuable. But then after we sort of evolved the transistor technology, because they wanted to support backwards compatibility, they just left it at 8. There are specific instructions in the x86 architecture, push all and pop all. These instructions assume a certain number of registers. Like push all, this was used for context switching. Push all says take all of the registers and push them all onto the stack. So if you want to switch from one process to the other, you would execute that instruction once, and then you could call into the operating system to say, okay, switch me with some other process. And the other process would find its registers in the stack and then would do a pop all. Now, if you go and you change the number of registers in your architecture, then you would have to re-implement this stuff to push all 16 registers and then pop all 16 registers. So they didn't want to do that. That's one of the reasons why they wanted to keep the registers with 8. So the other reason why you would want to keep the number of registers small is that it makes context switching easy. The less registers you have to do a context switch, the less you have to go into memory and store. So that's another reason. And the last reason was that if you want to incrementally speed up your program, you could simply add faster caches, memory caches, near your CPU to get similar kinds of execution speeds. And so that's what they ended up doing. Just make the caches faster and faster and closer to the CPU. And you can see in a die, and we saw a little bit on the Broadwell die, the cache is a pretty huge chunk of the processor. And if you go into one of those cores and zoom in, you'll see the L1 cache and L2 cache. They're pretty big chunks of the die space. That's the trade-off that they went for, rather than having a whole bunch of registers. Okay, let's see.
flexible having more like things you can do then rather than having a register more constrained?
Yeah, it's just easier in your design to be able to just make your cache faster. Change an instruction, changing your instruction set. That's hard. You don't want to do that too often. Okay, so the next thing I want to talk about are instructions. So a typical instruction in x86 acts on usually one or two operands, and they operate on this particular width. So here's an instruction: add quad RCX and RDX. This adds the contents of RCX into RDX. So the x86 architecture is what they call an accumulated architecture, meaning that you have two operands, and one of the operands also serves as the destination. Some architectures, like ARM, are 3-operand instructions, where you have a separate destination and 2 source operands. So x86 instead uses mostly 2. In x86, the size of the operand is denoted in the instruction and in the register labels. So this is a 64-bit instruction because the registers that you're using are the R, RCX, and RDX, and it's got a quad at the end of it. Add quad. This is a quad word, which is the 64-bit version. So Q is considered a quad word because at the time that we went from an 8-bit architecture to a 16-bit, we called the 8 bits a byte, and then we called the 16 bits a word. And then when we went from 16 to 32, we said, oh, that's a long word, or sometimes a double word. So then it's an add L for the mnemonic on the instruction. And then the last one is an add quad to say this is 4 times the 16 bits. So that's when you look at an instruction and you look at the last letter is telling you the width of the instruction. And these are all separate opcodes in x86. Okay, so here's a summary of the gas prefix and the width of the C data type that is used to operate on. So you see here, if you see an add B, that means you're adding 2 characters to each other in C. So when the compiler sees that you've declared a variable as a car, and then you're adding a number to that car, it's going to generate the add B instruction to do that addition. Likewise, if you have 2 longs and you're adding them together, the compiler is going to generate the add quad instruction when it compiles your program. So add quad, add long, add word, add byte. For the floats and the doubles, based on your data type, you're going to either do a single precision operation in the floating point unit or a double precision, S and D. And then extended precision is T. So these are the sort of the different the suffixes for these instructions. In terms of operands, I'm going to show you all the different types of operands in x86 instructions using the move instruction. So here is your example instruction is a move quad from source to destination. The 3 operand types are these. The first type is an immediate type, and this is a constant integer data type. And this is equivalent to, in your program, if you use a C constant, for example, hex 400 or negative 533, then in your assembly code, as an operand type, you'll see $hex 400 or negative 533. That's how it specifies that in the assembly instruction. And this immediate operand type this gets encoded directly into the opcode as part of the instruction when you include an actual immediate value as part of the instruction. Do you have a question or no? Another operand type is one of the registers. So you can use these registers directly as an operand type, one of the 16 registers. Typically, you would not use the stack pointer as a register that you use because you want the compiler to manage that. So this is something that you'll see how the compiler manages the stack pointer later. And then the last operand type is the memory address. And there's multiple modes of addressing memory. And the reason why there are multiple modes is because you have in your C program, you have arrays, you have structures, you have local variables, and accessing those requires a different kind of support from your CPU than simple than one. You want to support multiple ways of accessing memory. So that's what that is. So I'm going to go through examples of each of these modes and show you in the processor how these modes work. So the first one is your immediate value. And so if you have this assembly instruction, move $hex8000 into RAX. You could also have this thing move quad $array RAX. And if you had an array symbol in your program and it was located at hex 8000, then both of these two instructions would be exactly the same. And what it's going to do is it's going to take the constant hex 8000 and it's going to load it into RAX. All right, so that's the simplest mode of memory. Just load a constant into a destination. The next mode is also really easy. You take the register here, E sub A, and the operand value is whatever is stored in that register. And so when you do a move quad RCX into RAX, this takes the source RCX and moves it into RAX. I guess I didn't animate that, but it moves this value into that. All right. Yes, the original value stays in RCX. Yeah.
So it copies the bytes.
It copies the bytes, yeah. Okay, so the memory modes are where the action is, and this is where if you have a very small number of registers and you're relying upon accessing memory efficiently, which is what x86 is doing, then you need multiple ways of generating addresses very quickly. And that's basically what different memory modes allow you to do. I have a reference, say I have an array of structures, and I want to go to the 50th structure and access some element in that structure. I need to have a way of generating that address in one instruction, preferably in one or two instructions. I don't want to be sitting there calculating addresses, like 3 or 4 instructions calculating addresses and then accessing memory. So what memory modes allow you to do is to do all those address calculations in one step, or maybe 2. So this is what memory modes are for, and it's sort of a motivating why we have these things. So these are the main 4 types, the 4 different modes. There's the absolute mode, where you know the address of the data you're accessing, and this is just like a constant. You say, hey, I want that address location, whatever's there. Get me that. That's the simplest one. There's an indirect mode where I have an address in my register. I want you to follow that address and go into memory to where that thing points to, and then give me that operand. This is like dereferencing a pointer, where your pointer is stored in a register. So that's why that mode exists. You have a base plus displacement. So I have a base address, and I want to go a constant number of addresses away from that base address. So your base is stored in a register, and then you're doing an offset from that base. So if you have a struct in your program, and in that struct, maybe 12 bytes into that struct, you have a name, and say you want to access the name directly from that struct, well then doing base plus displacement makes sense because you know the displacement in the struct that you need to go, so you can get at it with one instruction using this memory mode. The last one is an indexed mode, and this is for array access. So with an index mode, if you are getting the 50th, say you have an array of integers and you want the 50th one, then typically what you would do is you would say, I'm going to load this register with 50, and I know the base address of my array is in another register. Then what I want you to do is I want you to scale that 50 to the size of the data element. So if I have an array of ints, then I want you to take 50 times 4, and then add it to the base address of the array, and give me that memory location. So that allows you to access an array element using one instruction. Well, you need an instruction to load the index register, but then one instruction to access it. So that's what indexed mode is going to allow you to do. So now I'm going to go through the specifics of each one of these modes. Are there any questions? Okay. This is like one of the most dry lectures of x86 that you'll get, but this is sort of like all these building blocks to actually get to the better stuff.
So all this we can implement directly to our code. Let's say you have a C program and you can actually type it in.
If you want to embed assembly into your
So
C
you
code, yeah, you could totally just you can directly program in assembly if you'd like.
And is the good programming practice in general?
Well, it depends.
I mean, I don't know.
It depends on it depends on what you're doing it for. Yeah, because if you're into one day, if you guys are programming scientific computations, and you're like, hey, most of the time it's in this inner loop, at like 95% of the time it's doing this one computation in this loop, then you could go and you look and you say, maybe you do need to hand code the assembly, just because I know something the compiler doesn't. That would be, and in fact, that's basically what assignment 3 is. You have this inner loop, and you're like, well, it's not using the instruction I want it to. I'm going to hand code the assembly to have it use the instructions, and then I'm going to use these modes. I think you'll use at least, you might use one of these modes for that. Yeah.
So does our compiler support assembly mnemonics, or do we have to insert it?
It supports assembly mnemonics, so you can insert gas assembly into the GCC compiler. So the GCC compiler is compiling your C code that has gas assembly embedded, and there's a language for specifying those instructions, and then it'll be embedded. Yeah. Yes. You have to tell it a particular way to mess around with it, actually, because eventually you have to connect up your assembly code with the variables in your C program. So we'll talk about that. With telling the compiler how to manage the registers so that it knows that you're going to overwrite certain things that it needs to save off before it calls your code. So yeah, bookkeeping. We'll get to that though. Okay, so I want to give you some memory modes. Here's the first memory mode. It's absolute. If you know the address that you want to access already, and it's a constant. So for example, when we talked about initialized global variables, and we say, hey, those are in the data section, and as soon as you load into memory, you know the actual virtual address of that variable. Then in the assembly code, you can just directly load that data using this hexadecimal, using the address of that variable. So that's what this does. So it says move quad. Because there's no $sign here, you're going to treat this as an address. You're going to go into main memory, and you're going to take whatever's at that address and move it into RAX. So this is a memory mode, and this is different than that immediate mode, which is just going to take hex 8000 and put it into that register. Similarly, without the $sign, a move quad array says, treat this symbol and go to the address of this symbol, assuming that it's at 8000, and then move whatever's at that memory location to RAX. Yeah.
Is this like machine memory?
This is your virtual memory. Yeah. Right. So yeah, and then this gets translated to machine. Yeah. So yeah, every address here is a virtual address. Yeah, we're not talking about physical addresses, just because I never see them. Like we have to have an oscilloscope, a digital multimeter, and we have to plug it, which is what people do actually. They're like, there's this attack called row hammer, where you have to know the physical address, because the idea is that if I hammer a real memory location around your real memory location, I can flip your bits. So that's what that attack is. And then these guys, I went to their talk. They're like, yeah, we were putting oscilloscope probes around the processor as it was running. People are like, you were doing what? They're like, yeah. He's like, we didn't shock ourselves too badly. But that's what you would have to do. To get the actual physical memory address bits, that's typically not something that you can easily get. But yeah, that's why this is all virtual. These are all virtual addresses for the sake of this discussion. Okay. All right. The next is indirect mode. So if you have a pointer in C, and then all of a sudden you say star P is equal to something, it's going to use indirect mode. And it's going to dereference that register. It's going to go to that register and dereference that pointer that's there and go to that memory location and access it. So move quad parentheses RCX into RAX. This is your source. You're going to treat this source, the RCX is a pointer. You're going to dereference it. So you're going to go into this register, treat this as an address, go to that memory location, and then take the data and move it into REX. All right, in direct mode. Base plus displacement. So here is your structure in memory. And the base of your structure is at hex 8000. Base plus displacement says, here's your base in RCX. It has an address, and the address is your hex 8000. Go 16 bytes from this address, add 16 to this register, then dereference that address that you calculate, and then move what's there into REX. So calculates this, 8000 plus, this is decimal 16. So this is actually going to go to 8010 and move the data there into REX. And you can see how if this was your structure and then you had an element that was a certain offset, you could see how the compiler would be like, oh, I know how to get at it in one instruction, rather than calculating an address and then dereferencing it with indirect mode.
You were talking about very specifically earlier, like if you had an int array, wouldn't you have to either put the size of the int array in part of that 16, or would you have to...
Oh, so we haven't gotten to arrays. This is for like structs,
Okay.
or simple offsets into a data structure. You would use this base plus displacement. And in fact, you'll see this a lot when we talk about function calls, because typically you would have a stack pointer, which is your frame of reference, and then you would do a displacement from that to get your function parameters and your local variables. So that's what this is used mostly for, that you'll see. But that's basically the idea behind this mode, to just make these accesses in one instruction rather than multiple ones. Okay, the last one is the scaled index mode, and this is the most general format. In fact, you could see that the rest of the memory modes are basically degenerate versions of scaled indexed, where these are basically not specified, or underspecified, I guess. And so the idea here is that you have a displacement, which is an immediate value. Well, it's a displacement. It's a constant. It's not a. I don't want to confuse the immediate term. This is just a displacement. You have a base register, as you did before in the previous mode. Then you have an index register. So this is for the arrays. So you would load 50 into that register if you were trying to get the 50th element. And then you have a scale factor, and this scale factor is typically a power of 2 based on the data type size that you're trying to index into. So this is why, and it supports 1, 2, 4, and 8, because we have char, which is 1, shorts, which are 2 bytes, ints, which are 4, and then longs, which are 8. So those are your different scales to choose from. And that's exactly because that's what you're doing. You're accessing an array of one of these basic data types, and so you're using this scale factor as an index. Yeah, so it's always a power of 2. And it's usually 1, 2, 4, or 8, and it corresponds to the data type sizes.
Oh, is that, so are you specifying the power, not the actual?
No, you're actually the actual number. Oh. So this is, 8 bytes. This is saying, 2 to the third, Okay. So here's an example. Well, this doesn't, let's see. So if you have a move quad 8, RDX is your base, RCX is your index register, and 8 is your scale. Then it's going to take 8 times RCX, which is decimal 24, add it to RDX, so this is 8024, which is 8018, I think, and then adds 8 to that. So this ends up giving you 8020 and putting it into REX. So this is like your base is here at 8000. Then this displacement 8 says, oh, my array starts here. So if you have a structure, and then the first element is a long integer, and your second thing is an array, then that's what this thing is doing. Bypass that first integer, and then scale an index register in RC at getting the third element of that array, and then return that value.
Is that the same for float arrays? Or do float arrays have to be implemented completely different size?
Same thing with floats.
But they're longer.
Well, that would be a double. So this would be double for for the double floating point format. You would have 8, and then for the single precision floating point, it would be 4.
Oh,
But same idea. Yeah, same idea. All right.
I'm dyslexic with all that.
Okay. Yeah. Back.
So RDX, that's the base. RCX is the displacement.
No, this is the displacement from 8.
Oh, that's the displacement.
And then RCX is your index register.
Okay.
So say the array started here at 8008, and I want to get the 0, 1, 2, third element of that. That's how it gets.
Okay, on RCX.
Yeah.
The index, does the index specify a specific number, or does the CPU or whatever read how many bits that specific address location?
The compiler is going to read it and say, so if you have struct dot array of 3, then it sees that in your code, and then before this move instruction, it will say move quad $3 into RCX, and then do this instruction. So really, there's 2 instructions to do this access. Actually, 3 instructions, because you have to actually load RDX also. So you have to load RDX, you have to load the index, and then you can do this move to access that element in that structure. Yeah.
So the RCX is an actual number, not like an array. It's not measuring how many bits in the array. It's like it's interpreting the X as a specific decimal number.
Yeah, as a specific value.
Right.
Yes. Yeah, and it's using that as your offset. Yeah. All right. Okay, so it was mentioned earlier that C is a very thin layer over your assembly code. And here is a picture of the translations between different memory modes and their C analogs. So here is your move quad. Your source can be either an immediate value, a register, or a memory location. And your destination could be either a register, a memory location, or a register or memory location. One of the things about x86 is that it does not allow memory-to-memory transfers, meaning that you can't have both operands be memory locations. One of them has to be a register, or a register or an immediate. So that's why you see when the source is a memory location, the destination has to be a register. Okay, so the first instruction, you're going to use the immediate mode, and you're going to move the constant hex 4 into RAX. This is the same as in your C program, setting a temporary variable, which is what RAX is representing, setting that to hex 4. So you've probably written that in your programs. If you have an immediate value and you store it in a memory location using parentheses RAX, this is like having a pointer P, a temporary pointer P that's loaded into RAX, and you dereferencing that pointer to store -147 into it. Okay. If you have a register-to-register move, so move quad RAX into RDX, this is the same as assigning a temporary variable to another temporary variable. The register to memory, where you're moving a register into parentheses RDX, this is like having the pointer P stored in RDX, and you're assigning what it points to a temporary variable. And then the last one, moving a memory location into a register. If you have parentheses RAX, this is like dereferencing a pointer P stored in RAX, getting the value that's there, and then moving it into a temporary register or temporary variable in RDX. So sort of one-to-one mapping between your assembly and your C program.
How reference works? I'm getting confused in general with reference. I don't want to talk about C++, but I know that C technically doesn't have reference, so we're kind of like emulating it. I'm not sure. I'm getting confused lately, and that's why I'm asking. Maybe I can understand. Like, when do you use first of all reference? Because I see that we use pointers, but when do you actually use it? And how it can translate?
In C, typically when we say reference to, it's always the address of.
Okay.
Yeah. It's always a virtual address that we're talking about when we say a
So
reference.
when you use that %, technically you're getting an address or the value. have a
When
percent.
it's getting the address
Okay.
and loading it into a variable.
Okay.
So before this, I had to say p is equal to the address of some integer.
Okay.
And then I can do star p is equal to negative 147 to change that integer into negative 147. And that's the level of indirection. And this is what makes C really hard to reason about. So this is exactly why you're having an issue with it. Because, this way of indirectly accessing memory is where,
Okay, so
and
you
this
go-
is where C, so that makes us unique in C. That's what makes it hard to
so
reason
it's
about.
indirectly accessed.
Yeah, because you're loading an address and then you're saying, this is holding an address, and then the operation is actually to follow that address and go to that memory location and use that as the operand. Or to use that as the thing that you're using, yeah.
Is this assuming that P and M are the same type for arbitrary?
This is assuming they're all longs, because they're all move quads. Yeah. All right. Let me quickly see. Okay, so I want to go through some examples of how these modes are used. If you see an instruction like this, add L 12 RBP into ECX, you see that this is a mix and match between 64-bit values and 32-bit values. The reason is that this is a memory location, right? That has to be 64-bit. You're specifying a memory mode, and the registers that you're using for that memory mode are 64-bit, but the actual instruction is a long word or a 32-bit value. And so what this does is says add the double word at this address, RBP plus 12, into ECX. And ECX is the bottom 32 bits of register C. Okay? Yeah.
Do you reference first or do you add both?
You add 12 to RBP and then you dereference. That's what base plus displacement does. Calculate the address that's an offset into it, and then dereference, basically get that memory location as an operand. Yeah.
Can you simulate extra registers by just using smaller bits, or just using the front half and bit mask, or not, and then bit shifting out the last four, and then only using? Does that make sense?
You could potentially do that, but the fact that the compiler is generating the proper bit width instructions makes it quite,
Yeah.
The compiler is going to automatically do these instructions for you. But what I sort of want to teach you is exactly what this means when you see it. And this is hard because you're mixing and matching different widths. Like the addresses could be a different are 64-bit, but the operands could be bytes or words or any arbitrary thing. This is why this jumble is being shown to you now, just because get you used to the way it's being encoded. No, none of this is on the midterm. Yeah, and by the time you get to the final, you'll have gotten used to this, hopefully, because you're reverse engineering binaries, and you'll be able. And I'm not going to give you this kind of stuff really. I'm going to give you the stuff that you usually see in reverse engineering. But I just want to give you this picture. Just it's more complete. So the next one says move byte, and this is a memory operation again because of the parentheses. And so because of that, you're operating on memory location, so you're using the RAX and RCX registers to calculate that address. And because it's a byte operation, your other operand, which is a register, has to be a byte operand as well. So %DL is the low byte of register RDX. So this instruction says move the byte at address RAX plus RCX into DL. So when you write your program, you have a car, and you have an address to that car that might be using this kind of mode. That's what this thing is doing. Subtract quad %RDX into RCX RAX 8. This says subtract the register RDX from the quad word stored at this address. This is a memory mode, and the address for this is 8 times RAX plus RCX. So that stores this register at that address. This inc word is an increment word, and the offset here, the displacement is actually given as a hex value, so this is like 10. This says increment the word at address 10 plus 8 times RCX. And you'll notice here that there's an operand here that's omitted. Anytime where you see this, you just assume that this is basically 0. So you'll see different modes where, like, for example, here, the index is missing, so you assume that that's 1. Here, the register is missing, so you just omit the register. So, yeah.
If you didn't put in that comma, how would that change?
I think it would be incorrect, because I think for this one, it requires 3 operands. So if you don't want to use it, you just have to, yeah. Whereas this one, it was okay without the scale. This is I don't want to teach you the ins and outs of someone's arbitrary assembler code parsing, but I believe this is okay. But if you got rid of this comma, it would not, which is unfortunate. But you could test it.
So does each instruction have its own default parameters for each word?
No, you have to specify exactly the mode, because these are encoded in bits of the instruction. So I'm not going to teach you instruction coding, but it's built into the opcodes for x86. So when x86 does an instruction decode, the bit patterns in the opcode tell you which mode to use, and then it actually maps into the execution of those instructions.
So your assembler determines which bit pattern
Yes.
based upon your
Based on what it knows from the Intel architecture manual. It's like, oh, I know that this has to go into a certain opcode. That's a table lookup in the Intel architecture manual, which is like 1,000 pages long. So, the poor assembler writers have
But
to.
based upon whether or not you admitted that, will it get different opcode, or will it?
It will know. It'll parse this,
Will it parse it and insert a value?
and it'll know what to do. Yeah, it'll assume a value. Yeah. All right. Okay, so some more, just to get you used to address computation walkthroughs. Here's some more examples. These are 2 registers. RDX has F1000, RCX has hex 100. If you see this as a operand, the address computation is to take RDX, add 8 to it, and then go to this memory address and get that what's there. This expression will add these 2 registers together, and then go to the memory location that results, F100. This instruction will take 4 times RCX and then add it to RDX. So 4 times RCX is 400, hex 400. And so you'll get this as an address, hex F400. You're all with me? That's good. And then the last one is add hex 80 to 2 times RDX. So 2 times RDX. RDX is up here. So when you multiply this by 2, you're basically shifting to the left by 1. So this ends up being 1E080. Yeah.
So the parens in the 3 arguments is the first 2 are added, the third one multiplies the second one.
This is scaled index mode without the base.
Yeah. Just trying to
Yeah, that's what
think
that.
of it as math.
Yeah.
Are those, in addition, is it casting it to a different type, or just adding them as
Unsigned. They're all unsigned because you're doing address arithmetic is always done unsigned. All right, finally, practice. I wanted to get to at least this. I want you to practice this. These are your operands on this column. These are the register state and the addresses. Generate the values, and this time I brought a ton of scrap paper, so whoever needs it. I've got plenty. You need some scrap paper? You're good? I'll just leave it here.
There you go.
Yes. Oh, you need scrap paper? Okay, so the first one is RAX. So the value is whatever's in RAX. So that's hex 100. This is the absolute memory mode, hex 108. This specifies an address that you go in memory to and return whatever's there, and what's there is hex AB. The dollar hex 108, this is your immediate mode. So treat this as a constant and then load that value. So this is hex 108. Parentheses RAX, this is your indirect mode. This says use the register here as an address, or take what's in RAX and use it as an address. Go to that address and give me the contents of memory there. So the contents of RAX is hex 100. And at your memory address 100, you have FF. So that's what you get. The next one is, this is the base plus displacement mode. You use RAX as a base. That's your base address, hex 100. You add 8 to it, makes it hex 108. And then you dereference that. So you go to hex 108, dereference it, and you get AB. The next one is RDX plus RAX plus 13. This is scaled index mode with displacement without the scale. So the scale is assumed to be 1. So then you add RDX to RAX. RDX plus RAX is 103. And then you add 13 to it. So 103 plus 13, this is like 116-ish.
Yeah.
But this is in hex. So this is actually 110. Because when you add 13 decimal to hex 103, you end up with hex 110. And this is where going back and forth between decimal and hex can throw you for a loop. But this is hex 110. You could put 0x, this is D, in front of it, and then it would be hex D plus hex 103, and then it would be a little clearer. But because this is a decimal, it makes it sketchier. So hex 110 is hex 13. Here's another one. This is decimal 260. And you add RCX to it, which is 1. And then you add RDX to it, which is 3. So this is 264 in decimal, which is hex 100 is 256. So this ends up being hex 108, which is AB. So 264, you subtract off 256, which is your hex 100. You're left with 8. So this ends up being hex 108 is the address you calculate here, which dereferences into AB. Yeah.
How much graph paper are we going to get on the calculator?
As many as you need.
Okay.
But for sure, if you can do this, then I know you can go back and forth between decimal and hex. That's what I'm looking for. And like if you get crazy addresses that are nowhere near this, then you know you did something wrong. Yeah. Like there is no 116 address here. Like if you made the mistake of, oh, I'll add 13 to 3 and get hex 116, and you'll be like, what happened? Well, that happened. So then that's a signal for you to say, okay, I'm going to recalculate. Here's another sketchy one. F8, and then you add 8 times RCX. So you're adding 8 to this. So F8 plus 8 is actually hex 100. So you can do this all in hex and get hex 100 is the address, and you dereference it to get hex FF. And then the last one is 8 times RDX, which is decimal 24.
Wait, so RCX plus 8 plus 0xF8 would be...
No, this is 8 times RCX. This is scaled index mode without the base, and then with the displacement. So this is 8 times RCX plus F8. And RCX is 1, so this is just 8 plus
So
XF8.
there is a third operand in the parentheses, then it's just addition?
This third one that's omitted is assumed to be null. Yeah. And then the last one is 8 times RDX, and this is decimal 24, and then you add it to hex 100, and this ends up being hex 118. So decimal 24 is hex 18. This is hex 11. All right, I am going to stop.